Welcome everybody to the first of what we hope to be a series of discussions known as the Beauty of series, where we delve into some fields of study and explore what truly make them interesting. This event, of course, due to these trying times, is hosted in a pre-recorded fashion. Um, so I hope everybody can accommodate for that.
All right, so for this talk, we will be exploring new ways to look at three different topics: series, graph theory, and discrete geometry. During this talk, feel free to pause the video to do the interactive problems or to go back to the downloadable slides to review them.
So let's take our time machine and journey back into ancient Greece and have a conversation with the philosopher known as Zeno. He imagined a sprinter running in a race. Well, the runner, he claimed, that first has to travel half of the distance to the finish line. Then, once he reaches the halfway point, he must travel half of that remaining distance, and then half of that remaining distance after that, and so on. So Zeno argued that if the runner always had to traverse half of the remaining distance, that means the sprinter would get infinitely close to the finish line, but he would always have half of the remaining distance to cross. So he would never be able to cross it. Therefore, he claimed it would be impossible for the runner to complete the race. Clearly, this statement is absurd. Well, runners complete races all the time. So can you find the fallacy in his argument? Zeno seemed to overlook the fact that the sum of an infinite number of values can be finite. How is this possible? Well, let's consider this following figure. We have a unit square, 1 by 1. That means it has an area of 1. And let's try to figure out how we can use this to point out the flaw in Zeno's paradox. Well, this square has it first divided in half. So we have a rectangle of area 1/2. Then the remaining half is divided in half yet again, which gives us 1/2 of 1/2, simply 1/4. Then we get 1/8, 1/16, 1/32, and so on. So with this combination of rectangles and squares, even though there are an infinite number of them, they somehow sum to a finite number, which is in this case, of course, 1. It's 1 by 1. So we can reduce Zeno's paradox into a simple equation. 1/2 plus 1/4 plus 1/8 plus 1/16 ... so on and so forth equals 1. Now we call this an infinite geometric series because it is the sum of an infinite number of terms, and the word geometric refers to the fact that consecutive terms have a common ratio. In this case, it's 1/2 because each term is, you multiply by 1/2 to get to the next one. Now the figure below proves yet another geometric series. Can you figure out the explanation? So if we break this down, we get 1/3 plus 1/9 plus 1/27, so on and so forth, equals 1/2. Using this diagram, let's consider just the green area for now. This first green rectangle over here is 1/3 of this unit square, right? Then we have 1/3 of 1/3, or 1/9, gives us this square right here. So that's 1/3 plus 1/9. Then this rectangle right here gives us 1/27 because it's 1/3 of 1/9. Then 1/9 of 1/9, or 1/81, and so on. So it kind of spirals in with this L-shaped sort of pattern. Notice that the red area equals the green area. So if the red and green are identical spirals and they sum to an area of 1, that means each individual one has an area of 1/2. It's another way of proving this equation right here. Likewise, we can apply this to another infinite geometric series, which is 1/4 plus 1/16, and etc. Let's consider, again, let's just consider the green squares. First, we have 1/4 of the unit square, which gives us this big green square right here. then 1/4 of 1/4 to get 1/16, then 1/4 of that remaining 1/16, so that'd be 1/64, and so on. Now we can see here that the red squares, the green squares, and the blue squares all have the same area, right? We can match them up. The red equals the green here, the red equals the green here, and so on. So if 3 different areas all equal each other and sum to an area of 1, that means each of the individual areas equals 1/3. Through these 3 examples, we have the following identities. 1/2 to the first power plus 1/2 to the second power plus 1/2 to the third power, and so on, equals 1/1. And you'll see later why I write it as this and not just 1. And of course, we have these two as well, dealing with the powers of 3 and the powers of 4, respectively. So let's try to extrapolate this pattern to the following series with the powers of 5 and the powers of 6. Well, the first thing we want to notice is that when we have the powers of 2 here, notice the denominator here is 1. Then powers of 3 here gives us a denominator of 2. Then powers of 4 give us a denominator of 3. So the denominator will always be 1 less than whatever the base is, whatever the power is. So naturally, that implies that 1/5 plus 1/25 plus 1/125 and so on will equal 1/4. And likewise, this bottom one will equal 1/5. So through our journey into geometric series, we've discovered that an infinite number of numbers can in fact add to a finite sum. And of course, runners can indeed finish races, contrary to what Zeno claimed.
All right, so the next topic that we are going to cover is graph theory. So a very famous problem in math is called the 7 bridges of Königsberg. And the problem goes like this. The center of the city of Königsberg was on an island in the middle of a river, which separated into 2 branches, as you can see on this map below. The city included 4 land masses, which were connected by 7 bridges that ran across this river. And the citizens of Königsberg wondered whether it was possible to travel around the city by crossing each of these bridges exactly once in one continuous path. Everyone who tried this ended up either skipping or recrossing at least one bridge. And after trying for a very long time, people began to assume that this was impossible, but they didn't know why it was impossible or how to prove this. So we can simplify this problem by drawing the land masses as dots, which we will call vertices, and the bridges as edges or lines, which connect these vertices. So the diagram we saw on the previous page was an example of a network. And this network is a figure with a set of vertices or nodes and a set of edges or lines that connect these 2 vertices, that connect 2 vertices. And the degree of a vertex is equal to the number of edges that connect to that vertex. So as you can see in this diagram, the leftmost vertex has 5 edges connecting to it. So we call that vertex of degree 5. Okay. A path that crosses every edge exactly once on a network is called an Eulerian path. Not surprisingly, it was Euler who discovered that a graph contains an Eulerian path if and only if there are either 0 or 2 vertices with an odd degree in that network. So in order to show this, we must first show that all graphs have an even number of odd vertices. So first, let's determine the sum of the degrees of all the nodes. We know that each edge connects 2 nodes. So for every edge we add in a network, we get +2 to the sum. And since we have all these +2s, we can conclude that S, or the sum, is even. So from here we can conclude that there must be an even number of odd vertices. So because if there are an odd number of odd vertices, well then we have two odds make an even, all the evens added to make an even. So then an odd number of odd vertices would make an odd sum, which contradicts the idea that S is even. So therefore there must be an even number of odd vertices. Let us consider the case where the graph contains only even vertices, like this graph below. So let's assume we start at any node, say node A, and we can take any edge to move on to another node, say node B. From there, we can move to another node and repeat. And since every node has an even degree, we will never get stuck because there will always be a path in and a path out. So for example, if we go to node D, we can go in and out. And then we could do the same for node E. And then going into node D, we go in and out, and that completes all the edges connected to node D. And then what we can do is just draw a path, an Euralian path that covers all the edges. Okay, so now let us consider a case where the graph contains two odd vertices. Based on our conclusion from the previous case, we know that every even node has a path in and a path out. So for an odd node or a vertex with an odd degree, you could potentially get stuck because because we will go in and then we won't have a way to go out. So thus, in order to complete an Euralian path, we must start at an odd vertex and end at an odd vertex. So in this graph, the vertexes with odd degrees are vertex E and vertex D. So let's say we start at vertex D, and since all the other nodes are even, then we can draw an Euralian path as long as we make sure to end at node E. So therefore, if we want to draw an Euralian path, we can't have more than two odd vertices in the network, or else we'll get stuck while trying to draw this path. So we can conclude that all graphs that contain an Euralian path must have either 0 or 2 odd vertices. But because the graph of the Königsberg bridges has 4 odd vertices, we know it cannot have an Euralian path according to our previous corollary because it has more than 2 odd vertices. So no matter how hard the citizens of Königsberg try, they will never be able to complete the path. And that is why it is impossible to walk across the city while crossing each of these bridges exactly once.
Okay, so to introduce the idea of de Bruijn sequences, I have a little challenge. Can we combine all of these pairs into one large sequence? So we could do it the obvious way, that is, just listing them out one by one. So the first pair is here, the second pair is at the end, and so on. But the problem with doing it like this is that there's overlap here, or there's excess rather. So there are 3 ones in a row. But to combine these pairs into one large sequence, the most we ever need is 2 ones in a row. And so we can make it a little bit more efficient by using what's called a de Bruijn sequence or a de Bruijn cycle. A de Bruijn cycle allows for this overlap, and in fact, it's the most efficient way. So the 0, 0 is here, the 0, 1 is here, the 1, 1 is here, and to make the 1, 0, we loop around to encode 1, 0. In this case, the de Bruijn sequence is so efficient that it halves the length of the sequence. The inefficient way has a length of 8, while the de Bruijn sequence has a length of 4. So how can we generate these de Bruijn cycles or de Bruijn sequences? Well, we can either do it through trial and error, or we can use what's called a de Bruijn graph. A de Bruijn graph is a really efficient way of encoding and finding these de Bruijn cycles and sequences. So taking a look at the graph on the left, we can follow the names of the edges to get the blue cycle. So the blue cycle starts on this node, and it traces there, and it follows this arrow. The arrow's name is 0, so we add a 0 to the blue sequence. Then we can continue. This edge is named 0, and the next edge is named 0, and we continue. This edge is named 1 until we've touched all of the nodes. Each one of these nodes has been hit by the blue sequence. And so we end up with this, which also happens to be a de Bruijn cycle. We can do a similar thing with the green sequence. The green sequence starts here at the top, and it traces paths which lie at 1, another 1, 1, 0, 1, and so on and we end up with 2 different possible de Bruijn cycles. Interestingly, both of these de Bruijn cycles encode for a subsequence of length 3. That is, they contain all possible combinations of 3 1s and 0s in a row. So they'll include 0, 0, 0, 1, 0, 1, 1, 1, 1, etc. The thing is, though, the 2 graphs on the left-hand side of the screen and the right-hand side are kind of the same. We both trace paths to generate the cycles. So the red one starts here, and we trace 0, 0, 0, 0, 0, 1, and so on. And it generates a different path. And this is still through tracing edges and finding their names. Not only that, the cycles on the left are shorter than the cycles on the right. This is because the cycle on the left has de Bruijn subsequences of length 3, which is to say that they include all possible 3-letter-long permutations of 0 and 1. But the cycle on the right has length 4. It's also interesting to note that the paths on the left go through every node once, while the path on the right goes through every edge once. Even though that they're the same graph, the cycles traced are different. We call the paths which go through every node Hamiltonian paths, and the path on the right-hand side, which goes through every edge, an Eulerian path. This Eulerian path is the same Eulerian path that we covered in the last section. So how do we generate these graphs? Well, starting from the first, most simple de Bruijn graph, we can exploit the property that the Eulerian paths are longer than the Hamiltonian paths. So we can take a look at its Hamiltonian paths. This graph's Hamiltonian path is pretty simple. Starting at A, there's only one other node to go through, C. And now we've gone through every single node. So we have the sequence AC in every node Hamiltonian path. On the other hand, its Eulerian path is longer. Starting at the node A, we can go C, which is here, C, here, A, and A. And that goes through every single edge once. This Eulerian path is longer. It has CCAA, and it turns out it encodes every possible length 2 word. The Hamiltonian path, which goes through every node, encodes every length 1 subsequence, and those are kind of obvious. You only have A and C. But the Eulerian path encodes every possible 2-letter permutation of C and A. So we have CC, AA, CA, and that loop, which is AC. Our Eulerian path, which goes through every single edge, is longer than our Hamiltonian path, and our Eulerian path has a longer subsequence. This means that the next de Bruijn graph will have a Hamiltonian path, which goes through every edge, CCAA. This means that this graph's Eulerian path, which is every edge, needs to turn into the next graph's Hamiltonian path, which goes through every node. So this Eulerian path, CCAA, needs to turn into the next graph's Hamiltonian path, so that the next graph's Hamiltonian path, which goes through every node, will have words of length 2, and the next graph's Eulerian path, which goes through every edge, will have words of length 3. So we've started with a Eulerian path, which is every edge, with words of length 2, and we've ended up with a Eulerian path with words of length 3. That means that wherever this graph has an edge, we want to turn it into a node, since this graph's Eulerian paths, which go through every edge, need to be isomorphic to or compared to the next graph's Hamiltonian path, which goes through every node. Every place where this graph has an edge, we need to turn it into a node. And so we can do it like this. So where this graph's C turns into the next graph's AC. This graph's C here turns into the next graph CC, and so on. This A turns into CA, this A turns into AA. Wherever the first graph has an edge, we turn it into the second graph's node. You'll also notice that the second graph's nodes are numbered with subsequences of length 2. So where the first graph has nodes of length 1, so just A or C, the second graph has nodes with length 2, AA or CC or CA. This reflects the fact that the second graph's Hamiltonian path, which goes through every node, has subsequences of length 2. So we can try one of these Hamiltonian paths. Starting at AA, we go C, and then C, and then A, and then another A. And this Hamiltonian path is the same as the first graph's Eulerian path. Both of them have subsequences of length 2. So simply by turning edges into nodes, we generate the next de Bruijn graph. We can see the same property here. Starting in the first graph, we start with all of the 4 edges turning into the next graph's 4 nodes. And we end up with the next graph having subsequences of length 2 compared to the first graph having subsequences of length 1. We repeat this pattern, exploiting the fact that the Eulerian paths, which go through every vertex, are always give de Bruijn cycles with a subsequence 1 greater than the path which goes through every node, its Hamiltonian path. The sequence continues, and we can end up with really complicated graphs really quickly by just starting from basics and changing every edge into a node. If you're interested in some applications of these de Bruijn graphs and the de Bruijn cycles, you can look at the lecture slides in the attached PDF, which go over one possible application, which is the decoding of DNA fragments into sequences. And that ends the presentation. Thank you for listening to our talk. This was the first presentation in the Beauty of series, and hopefully it won't be the last. We'll hopefully cover topics other than math, so if you have a field to suggest or if you know a person who might be able to give a similar presentation or a similar talk, please email us at hawthornorchard@gmail.com, Hawthorne spelled with an E at the end.